Hello, everybody. Welcome to another episode of Hacking with Friends. My name is Kody Kinsey. I'm a security researcher with Varonis, and this is my production gremlin, Michael.
Production gremlin? I got demoted again?
Sorry, junior, senior, executive, production assistant.
That's better.
Great. So today we're going to be talking about something that people love to get wrong on the internet. We're going to be talking about the difference between encoding, hashing, and encrypting. And
There's a difference.
Yeah, there is a difference. And I asked Michael about doing this earlier, and he was very nervous to do it initially. But after about an hour or so of review, I think that he's got a pretty solid grasp on it. So we're going to take a look at this from a Python perspective, because both of us know Python, and it's really easy to show off some of this stuff via Python. So if you know Python, you can also follow along with us to see some of these examples, or if you want to use some of this in your own coding. So Michael, what do you think is the difference between encryption, encoding, and hashing?
Let's see. So encryption is when you want to secure data and, for lack of a better word, encrypt it in such a way that people cannot read it. Whereas like hashing is where you want to secure data. So like maybe you're communicating over a radio signal, for instance, and some of that signal gets botched. You want to be able to make sure that you got all the data, so you would encode it in such a way that you would know if some of it was missing, I think. What was the third one you wanted?
Encoding, encryption, and hashing. So you did encrypting and hashing.
And then hashing, I know, has something to do with passwords. So I'm not really clear on what the difference between that and encryption would be. I'm just assuming it's some way to store data in such a... Yeah.
This is perfect, because that's actually... Most people that I ask that question, they're 100% sure when they start replying, and then as they start talking about it more, they become less and less sure about exactly how it all works. So fortunately, I've recently had to work with all of this, so I can explain it. And let's start with encoding. So encoding is basically a way of converting data into another format that makes it maybe easier for sending. And that's really what we're going to be focusing on in our one example today. We're going to be encoding into base 64, which is it's called URL safe way of sending data, because it doesn't have any nasty characters that might be strange and accidentally mess up some sort of transfer. This is a really common way that we see data be used, because if we're encoding just a string or some program maybe into a base 64 stream and sending it to another location, it just makes it very easy for us to encode and decode this data.
That actually comes up in my Python code later, is like when you're dealing with strings in Python, sometimes it needs to know what encoding format that character set is actually in.
Right, so encoding is about making things compatible. It's about transferring data into a format that might allow it to do something that it can't do in its current format, like be used in a piece of code that only accepts bytes, for example.
Or maybe you have like a text message with emojis and stuff in it, and I know that can really mess with, because like once you get into like the expanded emoji set and stuff, like that can mess with things sometimes.
Right, so on the most basic level, encoding is designed to convert one data format into another, but it is not a secret. There's no key, there's no like way that you could prevent an attacker from reading it, because it is an open format. That's the big thing about encoding that's kind of to remember. This is something where everybody can run this exact same one-line command and decode the data, because it's designed to be. It's not supposed to be a secret. Encoding isn't really, at least in the modern programming context, designed to be something that really hides anything. Maybe it'll do a little bit of obfuscation if you wanted to like have like a URL in malware that like might automatically be scanned by antivirus. But aside from that, like base 64 is generally used to just make data more easy to transfer. So that's generally what you'll see for various types of encoding schemes. They are not a secret, is really the big thing to remember. And they're not designed to store data securely, but they are designed to store data. So you put one thing in, you get one thing out. That's not the same with our next subject, which is hashing. So it's important to remember that difference. If you put a message into if you encode a message into base 64, you'll be able to get everything back.
So in some ways you could think of encoding as like repackaging, maybe? Like you're packaging it in a way that it's going to be more easily handled by other programs, right?
Yeah.
So you're not saying like, oh, you can never look in this package. You're just saying, hey, here's something that's easier for the shipper to handle.
Now, another example of this that I've encountered personally is radio transmissions. So you have analog versus digital radio transmissions. Digital radio transmissions are not a secret. You can just run a very simple program to decode them. And
Well, sometimes they are.
well, no, those are encrypted.
Yeah, encrypted. Okay, yeah.
Which is different.
Right.
Well, that's thing number 3. Good to note, though. So in Los Angeles, where I'm from, or at least I've been living for a while, the LAPD uses encoded but not encrypted radios, unless they're on their tactical channel where it actually is encrypted. And what that means is there are analog signals, which anybody can receive. There are digital signals, which you can receive, but then have to run through a decoder to get voice signals back out of. And this is more efficient, and most modern radios will tend to do this. And then there's encrypted channels for, tactical units, where it's critical that information not leak. And this is kind of the third thing, where the information's there, but the key that's kind of locked up the data is a secret. So does that kind of make sense for encoding? Do you think that you could explain encoding versus encryption now?
Wait, did we cover hashing?
Not yet. That's our third one.
Okay, because that's not the one. Yeah, the ones I'm confused about is encoding versus encryption versus hashing.
Yes.
Encoding, I understand.
Okay. But so you can now. My question was, you can now differentiate between. Explain to someone the difference between encoding and encryption.
Yeah.
Okay, cool.
Yeah.
So let's move on to our next one, which is hashing.
Mm-hmm.
Michael, you said it has something to do with passwords.
Or like, I know it's used in storing passwords. I think hashing is generally used in like securing data in some way, but I'm not like 100% sure like what.
Okay,
in what
so
sense.
Hashing is very different from the other things that we're going to be talking about today, because it in a way destroys data. If I were to take a really, 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 really long thing and I were to hash it, I would always get a hash that's like the same size.
Okay.
And what that means is I can try to brute force the hash. I can try to figure out what created this hash, but it is a one-way process. And that's really important to remember. A hash is a one-way process. These other two things we're talking about, encoding and encryption, are reversible processes. We put data in, we get it back out. When we put data into a hash, it's actually destroyed in a way because...
why would you ever want to destroy data? Why not just like delete data?
That's a great question. So if you have a circumstance where, let's say, let me provide a perfect dilemma for why hashing is important. Let's say that I have a website and I want people to sign up, put their username and password in, but I don't want them to get breached. If something happens to my website, I don't want their passwords to just go out there and have everyone available to see them. So I don't want to store the password, but I do need to make sure that I know that the user logging in has the right password. So what do? I take the password, I run it through a mathematical formula, or rather, I have basically a hash that runs a calculation as I feed it data, and then when I stop, when I'm done feeding it data, I get the value. And that value is unique to the piece of data I fed to it. So if the password is exactly the same and I compare the two hashes, then boom, I know that the person has input the same password, but I'm not storing the password directly.
So essentially, it's a way to preserve data where the owner doesn't know the data. So like as the website administrator, you wouldn't have access to that password, but when the user submits a password, you would be able to check if it is the correct password.
Yes, effectively think of it as a signature of the data. You're not storing the data, you're storing a signature of the data. So conversely, it's a little confusing because if you hear a lot about like hash like cracking or password cracking, and that is cracking a hash. But really what we're doing here is we're calculating a bunch of hash values and we're comparing them and see if we get a match. Because the probability of two different pieces of data creating the same hash is so incredibly small that the confidence is very high when we actually get a match like that.
Right.
So the whole point of a hash is that no two pieces of data should ever have the same hash. And if it happens, it's called a collision. And it means that particular hash has a weakness which can be exploited. So the literal actual thing that happens when we're going to be doing the code I wrote today is we're going to create a hash object. We're going to feed it data, and it's going to run it through this hash continuously until we're done. And then the digest value, or the value of that hash when we're done, is the unique signature for that piece of data. And that can be as big as a 5 gigabyte Ubuntu install, or as small as a single line of text. And a single line of text is usually what we're dealing with when we're storing something like a password. So we're going to look at a couple different things we can also do to make that a little bit more secure. So let's say that everybody knows that. So the difference between encoding and a hash is that the hash destroys data. Because if you think about it, everybody
No.
knows how, like a hash like SHA-256 works, because they can just, look up the Python library and run it. So it's not, data stored with a hash is not secret. Anybody who has a really big list of passwords that have been converted into hashes can immediately compare them, or they can use their computer's processing power to do the same thing. So if we want to be more secure about it, we can do something called adding a salt, which we'll talk about in my section, where we go into what adding a salt does, as well as we can change the number of times we run the operation on the data. So let's say that we want to make each piece of data that we are hashing really, really, really difficult to break. Well, we can run the hashing operation like 10,000 times on this piece of data so that it's computationally expensive and makes it really difficult for an attacker to go back and attack that piece of data and try to brute force it.
And so with salting, are you basically just putting in like bits of data that just are nonsense?
Yes.
They mean nothing, but because you're putting them, like, say, in the same location each time, you know to just remove that when you're comparing. Or wait, you wouldn't even need to remove them if you're putting in the same salt every time in the hash, then it's fine because you're going to get the same hash every time. But if they don't have that algorithm you're using to hash, then they can't.
That's exactly it.
Okay,
so salts are useful because it adds another layer. It basically adds like a password to the to the hash, sorry. So by using a salt in the hash, it results in something where if they don't have that salt, it becomes much more difficult to crack. Not impossible, it is definitely still possible, and I've seen it happen from a lot of different data breaches. But the average website will be secure, will have their database logins and passwords secured with a hash that includes a salt. And that is a bare minimum. If you're not doing that, then you're not keeping your customer's data secure. So like hashes are already, there's better ways of hashing data, which I'll get into, that include bcrypt, which actually don't always output the same number, but they're all computationally related to each other, so that with the program you can identify a hash that was derived from the same piece of data.
So is there a reason you wouldn't use a salt? Like, why would there be a website out there that wouldn't use a salt?
Because they're lazy, they don't know about them, or they don't care.
Did it come about later?
Yeah. So like first came like salts became much more popular as more websites got breached, and it became just expected that it was a necessary measure of security.
So you might see hashes without salts on older websites.
Right. So modern hashes, or really more secure hashes that are designed for storing passwords, like bcrypt, will have instead of always outputting the same number, like I said, they'll have a mathematical relationship between the different numbers it outputs. So if I'm an attacker and I'm attacking a bcrypt stored password, then the issue here is that like there could be an infinite number, well, not an infinite, but a whole giant number of different hashes that this is going to generate for the same piece of data. So there's not that one-to-one relationship that there is with other types of hashes. So I'll show off how you can kind of take this to the next level and be even more secure than using a salt when you're using a hash. So all right, now over to you. How would you describe encryption based on its differences from these other two types of data transmutation, I guess?
So basically kind of the way I was explaining things before, like encryption is when you want to take data and lock it up in such a way that either you can see it later, or maybe someone that you designate can see it later, but a third party could not. And this really goes into two camps. You have public and private keys, or symmetric and asymmetric encryption. So symmetric just means that both sides have the same key. So symmetric encryption is very good. Like, say for example, I just have a file on my computer. I'm afraid someone might access my computer and look at that file, and I wouldn't want that. So symmetric key encryption is very good for encrypting that file. It's very fast and efficient at that. However, the problem arises if I wanted to send Kody that file, because what I would have to do is somehow get Kody that same key that I encrypted it with, which obviously is a flaw in itself. And so that's why you get the other side of things, asymmetric encryption, and that's where you have the public and private keys. So for example, if I wanted to send Kody a encrypted file like that, I would generate these two keys. So I would keep my private key, and then, well,
So,
Yeah, so-
I would create a private key and generate a public key,
Yeah,
which
yeah,
I would
you
give
would
to
do-
Michael.
yeah.
Michael would take that public key and encrypt the file, and then
that's why I was about to correct myself.
Yeah.
Because the thing is, the receiver has to create the key pair. And then they would give the sender the public key. Now, the public key can be freely available to everyone on the internet, whoever wants to see it. And essentially, the way I understand it, it encrypts the file or the message or whatever in such a way that there's a very large number of possible solutions. And what the private key I hold allows me to do is know which one of those solutions is the correct one. So the metaphor that I heard that I helped me understand it was like prize doors. You know, you ever had that game where you like get pick the right door and you get the prize, right? Essentially, that's what the public key is doing, is just creating like thousands and thousands of these doors, and the private key is telling me, oh, it's behind door number 3, right? So that way it gives me the solution real quickly, and I don't have to. So obviously, you could attempt to brute force if you had the public key, but it's done in such a way that it would take hundreds of years with modern computing power to crack such a thing.
So yeah, the value of this is also, you'll see this for, sending secure email. I might create a public key that I make available to everyone so they can encrypt a piece of data or a message and send it to me. And nobody would be able to decrypt it. It would be encrypted kind of in a one-way function that allows me to be able to open it and see what's inside, but nobody else should be able to.
Now, a couple of points there. So it's very common, for example, for security researchers to have their public key freely available so people can send them messages securely, so on and so forth. However, computationally, it's less efficient. So that's why you will still see symmetric encryption much more commonly, just for, like I was saying, files on a computer. Also, another problem with the asymmetric encryption is that there's no way inherently to verify the sender. So I could get a message that says it's from Kody, but really it's from Bob, right? And there's no way inherent in asymmetric encryption for me to validate that it's from Kody. I would only be able to validate the message itself.
Could I sign it with my key?
Yes. Well, so I don't know about with the key, but there are digital signatures, and so that's a continuation. Another thing you can do, so you can attach a digital signature, and that addresses that problem. But so, for example, on Windows machines, what they actually do is combine symmetric and asymmetric encryption. So as I was saying, symmetric encryption is much more efficient and faster. So what they'll do is when you encrypt a file, it'll use symmetric encryption, and then that key that it's using is generated by asymmetric. So essentially, then I can share that public key and use the private key, and those keys combined will decrypt the symmetric key, and the symmetric key is what actually encrypted the file. If that makes sense.
Yeah. So one final example before we actually go and start demonstrating this is that ransomware likes to use public private key cryptography, because the ransomware, and we're actually going to be demonstrating this on a upcoming live stream, the person who authored the ransomware can have a private key that they generate public keys with that goes along with the ransomware. It encrypts everything with the public key, and then only the holder of the private key will ever be able to decrypt all the files and stuff that were encrypted on the person's system. And even if they were able, if the victim was able to intercept the public key, they still wouldn't be able to decrypt the files. So,
interesting point. I'm just hypothesizing here. But if you had the public key of the ransomware and you paid the ransom and got your files decrypted, could you take all of that information and combine it to derive the private key so that you could decrypt all the other files? I don't know if that's possible. There's probably a lot of like brute forcing here, but I'm thinking, because you would have the solution the correct solution, and you would have half the key. So you might actually be able.
There's a lot going on there. In actual ransomware, there's a lot of entropy that's generated on the machine. Like, depends on other things, but. All right, so let's start getting into some of the examples we have here today. I'm going to switch over to my screen, and we're going to take a look at encoding. And encoding is a pretty common practice in programming. If you are not familiar with it, I see it mostly when I'm exchanging information between a web server. It's a very common way of making sure that there's no errors. I use it personally to exfiltrate data to tracking servers. So also go ahead and try that out if you haven't done that yet. But doing this is very, very simple. In Python, I'm using, of course, Python 3. We can import base64, and that's virtually all we need to start encoding a string. The message I'm doing today is just this. This is the message I'm tossing around today. I make a variable that just contains that and print it, which you can see right here. And then once I convert it into bytes, which, Michael, do you know why it's important to convert it into bytes?
No, why?
Because these functions can't handle anything but bytes. So if you try to feed them a string, then it will choke on it and say that it doesn't know what it is. So to be sure that we're sending it the exact data that we want to, it insists that we convert it into bytes first.
I had that problem when I was writing my Python program for the first time for encryption. I was like, why would you take my string? And I was like, oh, oops, I gotta convert this, file to binary. Cool.
All right, so here in the next step, we're going to convert the bytes to base64. So we have the base64 message I'm creating. We just use the function base64.b64encode, and then my message, which is, of course, this one right here. And my message.encode will actually just encode it into bytes on the fly. So if we don't want to, actually convert it and then store it as a variable, we can just continue using that. So once I print the base64 message, I'll go ahead and run this. And if I scroll down here, I can see the base64 message looks like this. So base64 has these like 2 equal signs at the end. So you can very commonly just identify base64 from that. Again, very, very common to see in programming. But if we want to decode it, then there's no password required. This isn't like hashing. This isn't something that's designed to be like secure. We can just do print base64.b64 decode and then just base message. And this puts it into bytes. If we wanted to throw that back into a string, we could.
And so I could easily write a program using the same base64, and I would be able to decode that message. And anyone using base64 would be able to decode that message without like any further information.
Right, and something that I like to do is I have, for example, a Python script or MicroPython script that works on ESP8266 microcontrollers that preserves memory by just connecting to Wi-Fi, downloading like a big base64 payload from GitHub that contains lots and lots of Python functions, and it basically just runs the script that I have already stored up on GitHub as soon as it starts. So if someone was to take a look at the code that's on the ESP8266, there's nothing there. It's just asking for something from the internet. So there's not a lot of information there. And if I were to take down the server that it's downloading stuff from, then there really wouldn't be any trace of, well, I mean, you could go to the command logs. But if I was running my own server rather than GitHub, then it's a way that you could basically cut off access to a script that you have running on IoT devices. So I like it because it can just kind of unfold a bunch of commands that are all waiting in a base64 format. And I've used it extensively in MicroPython, for example, to be able to do that. I think you can do it in Arduino IDE as well.
And I think you alluded to this earlier, but this also would be maybe a rudimentary way to get around firewalls or other malware detection programs. It's just do some sort of simple encoding.
Yes, definitely. So one of the ways that malware authors will just add like one layer of obfuscation to their code is just base64 anything that's going to be too suspicious, because like if you're just running a very low level scan for malicious URLs or things like that, then you might miss it if it was encoded and you don't reverse that base64 string. So it adds another level of, I guess, competence an antivirus program has to have within it to know that it needs to identify base64 strings, reverse them, and then try to look for threats. And again, not everything is going to try to do that.
Yeah. I wonder if there's some kind of attack where, like, you can make your malware look like it's base64, so when it attempts to decode it, then, like, you attack, like, whatever program's decoding it.
The antivirus.
Yeah, exactly.
Maybe. All right, so let's take a look at the next example. So hashing is a little bit different. In order to work with the hash, we need to address it in a slightly different function, because we're basically creating something, adding something to it, and then checking on the value. So we're basically working with this a little bit differently than taking a piece of data and just converting it into something else. Because, really what we're looking at is the number that's stored in the hash function at the end of us pushing this data through it. So we're not really interested in anything besides that. And the way that we address this in code kind of reflects that. So again, we have our message that we're going to be working with. This is just a string, and we're going to convert it into bytes the exact same way we did before. But this time, I'll actually be nice and make a variable that's just called message bytes in order to hold our bytes from this text. So then we go ahead and create a hash object. So my hash equals hashlib.sha256. And if you want to work this yourself, you just need hashlib. I also imported random, but I don't think I actually used it in the code.
Yeah, you didn't.
So then within here, there's nothing at this point. There's nothing that we've actually passed to it, so it doesn't have any useful information. So we need to do what's called an update. So we can do my hash, which again is this variable right here, .update, and then we pass in the bytes that we want to hash. So in this case, we are passing in this string, which has been converted into bytes. And then we can print my hash.digest. So let me run this. And there we go. This is what we get. And if we want to do this in one line, we can also just basically do this function here, hashlib.sha256 message bytes. So of course we've already converted this into bytes, but we can also just do this too. I actually want to do this entirely in one line if we can. Decode .digest, and this kind of just does everything all together. There we go. See? So, oh wait. No, it didn't. I lied. Sorry. I'm going to go back, double check, see if it works. Oh, okay. There we go. So that's what happens when you're running the wrong program. It was running encoding. Okay, I was so confused. Okay, so here we can see the result of this being hashed. Michael, what does it look like to you?
Is that a lot of bytes or?
It sure is. I can also put this in hex. So if it looks a little cleaner, this is all, if we want to convert this one as well, we can do hex digest. And there we go. We can compare these two and we can see that they are the same. Now, again, the usefulness of a hash is basically to identify the same piece of data. So if I were to change anything in this message, then it would presumably change everything. So let's go ahead and try. So I'm going to do my message 1. Great. And I'm going to change this. The only thing I'm going to change is it's a period now. So let's go ahead and take the second one and do what I was trying to do before I realized I was in the wrong program and thought I was going insane. I'm going to do .decode to cast it into bytes. And let's see what happens. These should both be in hex.
Ooh, big ol' error.
String object doesn't like it. All right, fine. Oh, encode. Why am I dumb? Encode. There we go. Okay, so let's look at this. It does not look the slightest bit similar at all, does it?
No.
And if I want to change this back, let's make sure that I haven't done something weird in the code. If I just run the original, then look, these are perfectly identical. But then if I'm using the other message, it's totally different. And the reason that it's totally different is it's supposed to be wildly different if you change a single byte. So that's great. This means that basically the hashing is working. We're able to differentiate between a very small change. And this is also used for things like validating documents, downloads, like whatever it is. If you want to make sure that a piece of data hasn't changed at all, this is the best way to currently do it.
So is that why when you download certain programs, they'll give you like the hash and they're like, compare these hashes to make sure it's not malicious?
Exactly, because if a malicious author had changed a single byte of the file, then the hash would look completely different. You'd be like, whoa, that's not the same, and you should investigate further, because there are attacks that are done on installers and stuff like that, where people will go in and modify a file, upload it to a public community project, and then everybody who downloads it ends up being exploited through just a single program being modified a little bit in a way that nobody noticed. So it's always smart to just check the hash. It's a very simple thing to do. And yeah, this is a very easy way of verifying that data hasn't changed.
And so this hash you're doing right now, does it have a salt in it? Or?
No, it does not. So let's find out what happens if we don't use a hash in our salt.
Okay.
So here we're going to do a brute forcing attack. Why do I keep using random?
Those are some very leaked passwords right there.
Yep. So, all right, so let's demonstrate why exactly storing passwords as hashes can be bad. we're not going to write a very impressive Python script, but we're going to do some brute forcing anyway. So if we want to attack a hash, then we can create a list of candidates for what we think the hash was derived from. So in this case, we're going to create a list of passwords called passguess. And here you can see we have such great passwords as, the classics.
Yeah.
Admin, big password, the password, my password, password 123, password 321, and password 409. Now, we also need to actually create the hash for that we're going to compare this all against. So we're going to pick the password 321, and we're going to do the same function we've done before to turn it into bytes. So it's now known as message bytes. So, all right, this is where it comes down to this very, very short piece of Python code. For passwords in passguess, so for as many passwords as there are in here, if the result of feeding this into a hash digest equals the result of feeding the guess into the password digest, then print hash cracked and then the password. So if we get a match, basically the hashes are exactly the same between these two, then we're going to print out that it was a success. If not, then we're just going to print not this one. So let's go ahead and run this and see what happens. There we go.
Okay, I was going to say,
So
are
we
you
see
printing out the hash as you're trying
Not
it?
this one, not this one, not this one, not this one, not this one. Hash cracked, password 321.
Okay, nice.
So this is with a couple of lines of Python. Really, there's only like 1, 2, 3, 4, 5, like 6, 7 lines of like functional Python here. Like we can crack a hash very, very easily. And for things like Wi-Fi passwords, this is exactly the danger people get themselves into by reusing passwords and using really weak, simple passwords, because this is the exact process that hackers use to break into passwords on anything that relies on a hash that is vulnerable to this sort of attack. But I want to show you guys how you can make anything that you're working on that involves a hash much more secure by involving a salt or using a more modern hashing algorithm.
Yeah, because I was going to say, so this is basically what, John the Ripper and Hashcat are doing. And I know with those, in a real-world scenario, you would have, a multiple GPU machine just, processing, thousands or tens of thousands of these hashes a second.
Yep.
So it's not, it's not like you're trying, a handful and hoping you get lucky. You can really blaze through them.
Yeah, I have tested 1 billion passwords against a Wi-Fi have and shake before, and this computer got very hot, but it took like a day. So it's very, very possible to have your password broken if you are using a weak one and it's being stored as a hash. It's just a weakness of the way.
And I think that highlights too why you should change your password on a semi-regular basis, because in theory, if you never changed your password, then someone would have indefinite time to try to hack it, right?
This is true.
But even by just saying, okay, I'm going to change this every 3 months, that means they can't just sit a Raspberry Pi in their corner of their room trying to break that password, because it's not going to do it in enough time, right?
So there's other ways of trying to keep passwords that are stored as a hash more secure. And some of them involve a salt, and some of them, again, involve a salt. Some of them involve adding a salt, and some of them involve just bcrypt. So let's take a look at what happens when we run. We're just going to run the SHA-256 hash, but we're going to run it 5 times. So we have this very simple loop that's for I in range 0, 5, print the result of feeding in my message, which is a new message for this one.
Okay, so you're hashing it, and then you're hashing the hash. And
No, I'm just hashing it 5 times.
Oh, okay, gotcha.
So I'm taking the same hash and doing it 5 times. So what we'll see is, oops, it's still writing the last one. So what we'll see is right here, it does it super fast, and we see that it's the exact same every single time. So this is vulnerable to brute forcing. This is an issue. So what can we do? So if we want to prevent that, we can do a salt. So I'm going to add a salt it needs to be bytes. So in this case, it's just very salty. And if we want to do...
very salty in bytes.
Yeah, so if we want to do that, we can use a slightly different function. And what this allows me to do is pass in the hash that I'm using, so SHA-256, the message that I'm encoding, so this is just this one up here, and then the salt. So in this case, it's just very salty. But what's this?
It looks like an integer.
Yes, it is. So what that integer is doing is determining how many times we're running the hash. So in this case, they're all going to be the same. It's all going to be like 100,000. So it's running this piece of data through the SHA-256 algorithm 100,000 times before it stops.
That seems excessive.
It is. But the desire here is we want to make attempting to crack this computationally expensive for the attacker. So the more times we do this, the more times they have to for every individual guest. So let's go ahead. Well, oh, it's already done here. So here's a salted result. So if we want, so we can, actually, let me just scroll up. We can see that this is different from the one up above it. And the reason for that is because we added the salt. So adding a salt means that it prevents this sort of issue where we have the same thing over and over and over. But there is one thing that you'll notice here. If we were to run this again and again and again, it would actually, even with the salt, still present the same exact thing. So what else can we modify? Well, we have this other variable here. Yeah. So if I want to change the number of times that we're hashing
random.
Let's so right here we're going to do the exact same function we did before, but instead of saying 100,000 times, we're on each of these 5 times it goes around, we're going to generate a random number between 1,000 and 100,000. Is that 100? That's 10,000. Let's do 100,000.
Yeah.
So it's going to pick a random number between 10,000 and 100,000, and that's going to be the amount of times that it does this. So let's run it. And here. So we can see that these are all very different because we ran it through a different number of times. We've managed to get a varied result. So we can create a little bit of difference in the data that's coming out of this because maybe we want to add an additional layer of security to prevent an attacker from being able to figure out what information is in here. Now, of course, we can just use a completely different type.
Well, okay, so hash. Question though. If you're doing a random number of iterations over it, how would that be repeatable? So like,
it's not. You would have to have the same random seed.
Well, what I mean is, okay, so I do this to secure your password when you make a password on my website.
Right.
But then you come to log in again. How would I be able to check that if I don't know how many times I hashed that password?
Because you would need to have the same random seed. So if you were going to add this as a variable, then you would need to
save that random seed.
Okay, well, for one thing, it's a pseudo-random number. So a pseudo-random number means it looks random, but given the seed, it will actually generate the same number every time. Okay. So by using a pseudo-random number generator, then you can create something that seems to be random, but it's derived from the same seed. So as someone that wanted to implement this into your project, you could create a pseudo-random number generator that generates the same sequence of numbers depending on a seed, and that would be a good way of implementing the times that you're hashing into actually storing something like a password. Good question. Okay. So if we want to kick it up a notch, then we can just use something even better like bcrypt. So bcrypt was the subject of one of the first projects I did in computer science class when I was working in Python. And what it does is it uses a mathematical relationship between the number that's derived when you put in data to identify that it is actually from the same piece of data. So bcrypt will generate, let's go ahead and run it. And one thing I want you to notice is look at how long it takes to do the bcrypt hashing versus the other types of hashing.
Oh yeah.
It takes fully as long as the entire rest of the hashes we've done here. So even doing SHA-256 100,000 times, bcrypt is still slower. Now the reason for that is that we want it to be computationally expensive. That is a desirable property in this case.
So it makes it so I can't brute force it.
Yes. So if we're using SHA-256 to validate a program, perfect application, super short, unique, individual to that program. It's something where we're not trying to keep the signature of the program secret. We're trying to validate the data. In another application where we are trying to keep the contents of what we put through this hashing algorithm secret, then that doesn't really make sense because it's vulnerable. So if we use something like bcrypt, then we get here a completely different hash every time, but this is from the same piece of data, and we can use bcrypt to validate that every single one of these came from the same piece of data. So an attacker really doesn't have much leverage here. They can't, they can't directly attack this the same way they would SHA-256.
Right.
So hashing algorithms like bcrypt are much better for storing passwords, and you'll see that when a company is breached, if they even halfway have their stuff together, usually they put out a message like, "Not to be feared, everyone. We encrypted all the passwords with bcrypt," and they're just like, "Oh my god, great."
Yeah.
But I mean, fundamentally, it is better for them to try to store this data with something like bcrypt rather than just with SHA-256. It's just not the right hashing algorithm for this kind of work.
Yeah, and I do know, like earlier I was alluding to the fact that if someone was trying to brute force, they would often use like GPUs or FPGAs. But from what I understand, I don't know if it's Bcrypt or other algorithms, but there are algorithms out there intentionally designed so that they can't be used on that sort of hardware. They have to be used on the CPU because they're slower and involve more complex processes.
Yes, if you want to keep something from being reversed as a hash, it is very desirable that the hash be computationally expensive. The longer it takes for each guess and the more processing power, the less likely it is that someone is going to want to sink the time and the work into attempting to crack it.
Well, yeah, in the sense that for security, you want it more computationally complex. But, if I'm running Facebook and I have thousands of people logging in every, second, it probably it's going to take a lot of computing power on your servers to handle that, but that's a price maybe you need to consider. Is your user security worth that, right?
Yeah, SHA-256 1 million times with assault, then put through Bcrypt.
Okay, that's a little excessive.
There you go. Better safe than sorry is what I say. All right, so I feel like we've gone really well through hashing, which is great because I feel like it's not a subject that's explained very often or very well. So let's go into encryption and explain that encryption shares some properties with hashing, only it's non-destructive. Like encoding, it is designed to actually recreate the data completely, but unlike hashing, or rather unlike encoding, it is designed for the key to this to be a secret. And also it has the secondary goal to try to look as much like entropy as possible. So encryption has two goals, really, if you want to boil it down into its core, I guess, things it needs to do. It needs to, for one, be able to recreate the data, and for two, look as much like random noise as possible at all. And if you can do that, then you have a good encryption scheme that will probably be difficult to reverse, provided that the password you use to encrypt it is hard to guess. Right. So, Michael, I believe you made some examples to show us the different types of encryption.
Well, I have one example of using Python to encrypt I can show. So basically, there are a multitude of Python libraries available for encryption. Today, I'm just kind of showcasing one of them. That's the cryptography library. There is also PyCrypt, which is a little more versatile and has a lot more stuff, but this one was a lot easier for me to implement on the fly easily. And essentially all I did is created a definition. I have two definitions. But the first definition is the main one as far as encryption. And all you have to do is you read in a file or message in bytes, which was a problem I had at first. Because I was just like, oh, here, take my file, encrypt it. It's like, no, I don't want to take your file, actually. So if you can see here, that's why I had to use the RB, so that's read bytes. Because originally I just had R, and I was like, why isn't, no, this isn't working. So you read it in the bytes, and then I send it up here to this definition. And essentially all I call is fairnet, which is just a implementation of the symmetric encryption. And so this is only using a single key. So this is great. I have a couple of files on my computer. I want to secure them. Something to be mindful of is with the way I wrote this Python program, but then also on top of that, with the way this Python library is written, it all happens in memory. So it's more secure that way. But then also that means that you can't encrypt files that are larger than the amount of memory that you have available. So, I'm not going to be, encrypting a terabyte at a time. Like, I'm not going to do full disk encryption this way.
Right. Although I would say that if you had another hour or two, I'm sure you could chunk the data and do it in sections.
Yeah, you could probably chunk the data in certain ways and do that. That would definitely be a solution. But yeah, so one of the first things I do is... this is the decode one. It's down here, I generate the key. Now, obviously, you would want to keep this somewhere secure because anyone with this key would be able to decrypt your file, right? So, for example, you might want to put it on a flash drive that you keep on you that is password protected or something like that. But yeah, so you can just generate the key, and then you say, here's my binary data, encrypt it. Now, the way these programs can work are there's the stream ciphers and block ciphers. So a stream cipher would basically take each byte of data and encrypt it a byte at a time. However, that's kind of fallen out of favor in fashion. And so now what we do would be the block cipher. So that's where you take a block of data, so say 128 bytes or bits, and encrypt that as a block and then move on to the next block.
That makes sense.
So, for example, you may have heard of AES a lot. Advanced Encryption Standard, I think is what it stands for. So essentially that's what it's doing. It's taking 128-bit blocks of data and encrypting that at once. And not to get super math nerdy, but essentially all it does is it lines that up in a 4x4 grid, and then it substitutes bytes and shifts them around and combines them with a key in such a fashion that, without that key, you could never get that data back. So I can show you this in action real quick. So I have this test folder here with, screenshot of my code going on, super secret, very valuable Python code here. And so if I run main2,
make sure you're running the right code.
Yeah. Sorry, some of this is repurposed older code. So, but yeah. So, oh yeah, that's right. I sent the key to my email in this one because I was reusing some older code.
Ransomware code.
Yeah,
for our next live stream.
Some ransomware code that I was repurposing here. But if you go back to this image, you can now see that it's gone picture. It's done for. But we can revive it. So essentially, I just made another program here. Decode. It basically just does the same thing in reverse. So it reads the file in binary, and then it takes the key and it will decrypt it. And it literally, like, these two lines here is basically as simple as it is. I can even show you, like, all of this can be done. If you wanted to implement encryption, an encrypting file, this is all you need. You import cryptography, you save the key variable, and then you import that in to the library so it knows what key it's using, and then you encrypt. And then in another program, you would do the same, but instead of generating the key, you just load in the key and decrypt it. I'm going to switch away from my screen for a second and go retrieve the key. But I think I'm logged in on this one still.
Yeah, so I also, while we're waiting, have some code that I'm not going to go into yet too much. But this is some code that is involving public-private key encryption that is going to be for the next live stream. So I believe that Michael is going to be showing off what public versus private key encryption looks like. But essentially what we're going to do is we're going to encrypt a bunch of files using a public key, and then we're going to show off that with the private key, you can go ahead and decrypt all of these just fine. So really cool, but I believe Michael's almost done typing passwords.
Yeah, I'm loading in my email right now.
By the way, your code said error, email not sent.
Oh, did it?
Yeah.
Oh yeah. Okay. Well, I assure you that will work. It will return the file. I can do this. How about I just make a new screenshot and have it print the key. We go back to my screen. So I'll just print key. Cool. And I'm going to take another screenshot here just so we have something to encrypt. And There you are, screenshot. Okay. Now if we run this again, cool. We get this key. So the full thing isn't actually the key. That's just, the key is this part, just because of the quick way I implemented that.
Oh yeah, it's just bytes.
It's just saying this
the
is...
key's returning is bytes.
Bytes, yeah, exactly.
Cool.
So now if I run decode, it'll ask me for the key. I should be able... Wait, before I run it though, I'll show you that.
Yeah, let's see that this screenshot is locked down.
They're both locked. Now this isn't going to decrypt both of them, just because the other one was previously encrypted and I didn't delete it. What?
Error. No such file or device.
Oh.
Liar.
Oh yeah, no,
Betrayer.
no.
This will be reported.
Where can I say? Here, let me... This is very dirty. But, yeah. I need... Because I originally wrote this code on my Windows machine.
Oh,
so
your decode is in the wrong location.
Yeah, exactly.
Does it save as a JPEG or as a PNG, you dirty recoder?
That's a good question.
I just like to pay attention to detail.
I should have tested this more.
No, it says in your other code too.
Oh, does it?
Yeah, this one. It says
PNG.
Yeah.
Good catch.
Thanks.
What would I do without
This is why we have the big monitor so I can see the code, because before I couldn't see anything.
Okay, so now if we run decode,
what's the key?
That's why I pasted that over here.
Nice. Is that equal sign part of it?
Yes.
Oh.
Turn. Cool.
No errors. Okay.
Yeah, no errors. Let's see if that worked. If that didn't work, I need to move the equal sign over.
Hey, you got it. Okay, cool. So
yeah.
You encrypted and then decrypted a file.
Yes, I know. I'm here all week.
Congratulations. It's such
answer all your questions.
Beautiful work. You also had some random keys sent to your email, and there's some other stuff going on too. But all in all, I think it's a good demonstration of the differences between these different types of data transmutations.
And we are basically out of time. So unfortunately, you don't get to see asymmetric encryption. But basically, it would just be the same thing. But instead of getting the one key, you would get the two keys, and you would send that public key out.
It's what's on my screen right now.
Yeah.
So for our next live stream, we're going to jump into public-private key cryptography in the context of ransomware. So we're going to be explaining it exhaustively. So don't feel too bad that you missed it. Just tune into the next live stream we're going to be doing, which is either going to be that or our other live stream with Killian. I guess we'll see. Yeah. But stay tuned, and you will get to see how this kind of cryptography can be used for all sorts of nasty stuff. So anyway, big thank you to Varonis for sponsoring this and making this a thing. If you enjoy this content, make sure to also check out the other free stuff they have, such as the PowerShell AD course. If you're going to be doing anything with Active Directory, it's great to know how to do it with PowerShell. So I think you'll find that it is a really great resource if that's the work you got to do.
Yeah.
And
even get you some CVE credits, whatever credits.
CP, yeah.
CPE.
Yeah. You'll also be able to get some great CPE credits.
Yeah.
So, thank you again for hanging out with us while we're going all through all this great stuff. Again, I think this is a topic that hasn't really been covered very well.
Thanks for bearing with me while I fixed my shoddy Python code there.
But yeah, if you guys have suggestions for upcoming episodes, if you like this, if you have any ideas for how maybe we can do something else with hashing or maybe go more into depth with cracking, then please let us know. You can hit me up on Twitter at Kody Kinsey. I'd love to hear your feedback. Michael, I believe you're _Hoyd
on Twitter.
Michael's full legal name.
Yes.
And we will see you guys next time. Thank you. Bye.